This is a continuation, part 2 of our topic, conservation of energy. Topic number 4. If you can recall, by the end of this topic, you should be able to apply the mass equation to balance the incoming and outgoing flow rates in a flow system. Recognize various forms of mechanical energy and work with energy conversion efficiencies, and understand the use and limitations of the Bernoulli equation and apply it to solve a variety of fluid flow problems. And work with the energy equation expressed in terms of heads and use it to determine turbine power output and pumping power requirements. In our previous discussion, we already tackled the conservation laws, mechanical energy and efficiency, and the continuity equation. Today, we will be discussing about the Bernoulli equation and the general energy equation. So let's start first with the Bernoulli equation. So what is the Bernoulli equation? So Bernoulli equation, despite its simplicity, it has been proven to be a very powerful tool in fluid mechanics. In this section, we shall find out what Bernoulli equation is and how it was derived using the conservation of linear momentum principle. And we will also demonstrate both its usefulness as well as its limitation. So to start with, this Bernoulli equation is an approximate relation between pressure, velocity, and elevation. So as you can see, it's just similar to our other equation and is valid in regions of steady, incompressible flow where net frictional forces are negligible. So take note of the term steady and incompressible flow. So this equation is only valid for those regions experiencing this kind of flow. It is derived by applying the conservation of linear momentum. It is an approximation that applies only to inviscid regions of flow. So when we say inviscid regions, so meaning we can neglect the viscous effects. So as you can see here, for example, in this flow, we can see that the Bernoulli equation is an approximate equation that is only valid in inviscid region of flow where net viscous forces are negligibly small compared to the inertial, gravitational, or pressure forces. These kind of regions occur outside of the boundary layers and wicks. So as you can see here, in this if this is a foil, for example, along here there is a flow of a fluid, Bernoulli equation is only valid in the streamline, but it's not valid here in the region where it is not inviscid. The Bernoulli equation is obtained from the conservation of momentum for a fluid particle moving along a streamline. It can also be obtained from the first law of thermodynamics applied to a steady flow system. This equation is an expression of the mechanical energy balance, which states that the sum of the kinetic, potential, and flow energies of a fluid particle is constant along a streamline during steady flow when the compressibility and frictional effects are negligible. So for steady flow, incompressible flow, the Bernoulli equation is expressed as the pressure divided by rho plus v squared over 2 plus gravitational constant multiplied by the elevation. And this is constant along a streamline according to the Bernoulli equation applied to steady flow, incompressible flow. For 2 points experiencing steady flow and incompressible flow, our equation would be equals to P1 over rho plus V1 squared over 2 plus JZ1 is equals to P2 over rho plus V2 squared over 2 plus JZ2. For unsteady flow, compressible flow, our equation would be expressed in this form as you can see in the presentation. Because here now, for unsteady and compressible flow, there would be a change in pressure with respect to density and also change in the velocity of the fluid with respect to time. The kinetic, potential, and flow energies are the mechanical forms of energy as discussed in the previous topic. And the Bernoulli equation can be viewed as the conservation of mechanical energy principle, because as you can see here, each term of the Bernoulli equation is actually the mechanical energy, which is the flow energy, kinetic energy, and potential energy. So this means that this equation is just an equation that is viewed as a conservation of mechanical energy principle. The Bernoulli equation states that the sum of the flow, kinetic, and potential energies of a fluid particle along a streamline is constant. Therefore, the kinetic and potential energies of the fluid can be converted to flow energy and vice versa during the flow, which causes the pressure to change. This phenomenon can be made more visible by multiplying the Bernoulli equation by the density. So as you can see here, if we multiply our Bernoulli equation with the density, it would become this kind of form. We have pressure plus rho v squared over 2 plus rho gz, and this is still constant along a streamline. So this equation now has a unit of Pascal, since P here would be in Pascal. So when you multiply the basic Bernoulli equation by density, this will be the corresponding equation that we will obtain. Each of this term here of this equation has a meaning. So P here represents the static pressure. The static pressure does not incorporate any dynamic effects. It represents the actual thermodynamic pressure of a fluid, which is used in thermodynamics. So if you check the tables, steam table for example, the pressure that you can get there is the static pressure. The quantity or term rho v squared over 2 is the dynamic pressure. It represents the pressure rise when the fluid in motion is brought to a stop isentropically. And then the last term, rho z, is the hydrostatic pressure. So it is not a pressure actually in a real sense, since its value depends on the reference level selected. So it depends where your reference level, where would be the ground or the point where the elevation would be 0, because you can actually choose that. So the sum of the static, dynamic, and hydrostatic pressure is called the total pressure. Therefore, the Bernoulli equation states that the total pressure along a streamline is constant. Also, the summation of the first term, which is our static pressure, and the dynamic pressure is what we call the stagnation pressure. So this is the sum of the static and the dynamic pressures, the first and the second term. It represents the pressure at a point where the fluid is brought to a complete stop isentropically. So that's why it's called stagnation. So how do we illustrate this? So as you can see here, we can see a liquid rise in this is a piezometer. The first tube is a piezometer tube, and then the second one is a pitot tube. So we have a piezometer and then we have a pitot tube. The liquid rise in the piezometer tube to a column height or head that is proportional to the pressure being measured. If the pressure is to be measured below the atmosphere, or if measuring the pressures in gases, for example, piezometer tube does not work. So however, the static pressure tap as well as the pitot tube can still be used, but they must be connected to some other kind of pressure measurement device, such as a U-tube manometer or a pressure transducer. As you can see here, the relationship between the static, dynamic, and the hydrostatic pressure can be seen. So the one that you can measure using the piezometer is the static pressure. That's the P. And the one that you can measure using the pitot tube is you can get here actually the both the stagnation pressure, but you can also get the dynamic pressure, because the difference between the measurement is the dynamic pressure. So the measurement here and then the measurement here is the dynamic pressure. So when the static and stagnation pressures are measured at a specified location, the fluid velocity at that location can be calculated using this formula that you can see here. So it's just V is equals to the square root of 2 stagnation pressure minus the static pressure divided by the density. So the stagnation point is this point here wherein the fluid will be made to stop isentropically in order to measure its pressure. So the pressure that you will measure is the stagnation pressure, or the P stat. So again, the static pressure tap measures the static pressure. The pitot tube measures the stagnation pressure, and the piezometer tube can be attached to the pressure tap and to the pitot tube in situations in which the static and the stagnation pressures of a flowing fluid are greater than the atmospheric pressure. So as you can see here, we're able to, if that is the case, then we can actually use a piezometer tube. So when this situation arises. So in this slide, you can see the streamline. So the point here that has no velocity at all is what we call the stagnation streamline. So the streak lines produced by the colored fluid introduced upstream of an airfoil, for example, since the flow is steady, the streak lines are the same as the streamlines and the path lines. The stagnation streamline is marked here in this flow. So the Bernoulli equation is one of the most frequently used, however, it's also the most misused equation in fluid mechanics. Its versatility and simplicity and ease of use make it a very valuable tool for use in the analysis, but the same attributes also make it very tempting to misuse. So therefore, it's important for us to understand the restrictions on its applicability and observe the limitations. So the limitations on the use of the Bernoulli equations are: first, it is only limited for steady flow. So it should not be used during the transient startup and shutdown periods, or during periods of change in flow conditions, because those kinds of situations introduces a unsteady flow. So only when the flow of the fluid is already steady. So during the startup and shutdown periods, it is expected that the fluid does not experience a steady flow. It's also valid only for frictionless flow. The frictional effects are negligible for short flow sections with large cross sections, especially at a low flow velocity. So for example, you have a large ductings but very short length, then the frictional effects in that scenario can be neglected. Thus, you can apply the Bernoulli equation. Also, the frictional effects would be significant in long as well as narrow flow passages. So in the weak regions downstream of an object, in diverging flow sections such as diffusers and near solid surfaces. So you cannot apply the Bernoulli equation in those situations. A component that disturbs the streamlined structure of flow and thus causes considerable mixing and backflow, such as a sharp entrance of a tube or a partially closed valve in a flow section, can make the Bernoulli equation also inapplicable, because it would distort the streamlined structure of the flow. Also, it cannot be used when there is a shaft work, so meaning it will only be used when there is no shaft work. So not applicable in a flow section that involves a pump, a turbine, a fan, or any other machine or impeller. But because these devices destroy the streamlines and carry out energy interactions with the fluid particles, because as you can remember, the pump increases the energy of the fluid while a turbine extracts, so meaning there's already a change in its energy, therefore there's also a change in its streamline or flow. So the Bernoulli equation can be applied relate to a flow section prior to a past or past a machine. So before the machine or after the machine, then you can apply the Bernoulli equation, but not when the motor, fan, these machines are found along the stream or along the flow. Another limitation is that it is only applicable for incompressible flow, because this means that the density is constant. It is satisfied by liquid and by gases at Mach numbers less than 0.3, since compressibility effects and thus density variations of gases are negligible at these relatively low velocities. Also, it's only applicable for situations where there is no heat transfer, because the density of the gas is inversely proportional to the temperature. So if there is a change in temperature, the Bernoulli equation should not be used for flow sections that involve significant temperature change, such as heating or cooling sections. Finally, it's applicable for flow along a streamline. So it is also applicable to across the streamline and applicable between any points in the irrotational region of the flow. So to illustrate those limitations, so as you can see here, at this section, for example, of a ducting, from point 1 to point 2, there is a sudden expansion. So meaning, at this point, the speed would be restricted, because if you can remember, if the cross section is less, the speed would be greater, right? Because it would restrict the flow. But here, since you increase the cross section, there would be a sudden expansion. There would be a sudden also decrease in the speed. So I mean, there's a change already in the streamline. So that's why you cannot apply the Bernoulli equation. It should be a steady flow. As you can see here in this long and narrow tubes, there is a great possibility that there would be frictions along this flow. So that's why it has to be a short and has a tube with a wider area for us to apply the Bernoulli equation. So it should be a frictionless flow. And then you can see here in this valve, there is actually a restriction of flow, meaning it disturbs the streamline. So therefore, it also is not, we cannot also apply Bernoulli equation in that case. And in this scenario here, there is an introduction of a fan, which is a machine. So there should be no shaft work. So that's why you cannot apply Bernoulli equation there. And here there is a heating section in the ductings, so meaning there is already a heating or cooling effect, so there should be no heat transfer. And in here you can only apply during the streamlines and not in the wakes. So that is basically the limitation of the Bernoulli equation. But there are instances that we will apply this equation to those situations for us to know the maximum or the minimum scenario. Another important term here that is related to Bernoulli equation are the hydraulic grade line and the energy grade line. So it is often convenient to represent the level of mechanical energy graphically using heights to facilitate visualization of the various terms of the Bernoulli equation. So this is done by dividing each term of the Bernoulli equation by acceleration due to gravity. So if you can still remember the basic Bernoulli equation, when you divide it by gravity, we would obtain this equation. So we divide each term by gravity. So each of the term of this equation now has a unit of meter or feet. So it's in length, because as you can see, z here is actually in meter already, or feet. So each of these terms would have the same unit. So the first quantity here is the pressure head. So it represents the height of a fluid column that produces the static pressure. The v squared over 2g is the velocity head. It represents the elevation need for a fluid to reach the velocity v using the frictionless free fall. And the last term z is the elevation head, and it represents the potential energy of the fluid. In this equation, h is the total head for the flow. So the summation of the pressure head, the velocity head, and the elevation head is the total head for the flow. Therefore, the Bernoulli equation can be expressed in terms of heads, as the sum of the pressure, velocity, and elevation heads along the streamline. So these are constant during steady flow when the compressibility and frictional effects are again negligible. So these are the quantities that will help us define the hydraulic grade line and the energy grade line. So as you can see, this is an alternative form of the Bernoulli equation expressed in terms of heads. The pressure head, velocity head, elevation head. The sum is the total head, and it should be constant along a streamline. The sum of the first and the last term, which is the static and the elevation head, so static head and the elevation head, is what we call the hydraulic grade line. On the other hand, it represents the line that is the sum again of the static pressure and the elevation head. The sum of the three terms is what we call the energy grade line. So H could also be the energy grade line here. So as you can see, the difference between the energy grade line and the hydraulic grade line is the dynamic head, which is the V squared over 2G. So to illustrate the difference between the hydraulic grade line and the energy grade lines, as you can see here, this is for a free discharge from a reservoir through a horizontal pipe with a diffuser. So there is a variation of the hydraulic grade line and energy grade line along the flow. So you can see here, this arrow represents the hydraulic grade line, and this dotted line here, this broken line, represents the hydraulic grade line, and then this solid represents the energy grade line. The difference between them is the dynamic head, or the V squared over 2G. So to illustrate further, you can see here how the energy grade line, the hydraulic grade line, helps us visualize the mechanical energy. So a steep jump occurs in the energy grade line and the hydraulic grade line whenever the mechanical energy is added to the fluid by a pump, and it also experiences a steep drop across whenever the mechanical energy is removed from the fluid by the turbine. So here, because there is an introduction of the pump, as you can see, there is an increase in the energy grade and the hydraulic grade line. And here, since this is a turbine, there's a sudden decrease in the energy grade line and hydraulic grade line of the fluid, because what the turbine does is to extract energy from the fluid. So in that way, we can visualize the energies. So you can see here also the pressure gauge of a fluid would be 0 at the locations where the hydraulic grade line intersect the fluid, and the pressure is negative or vacuum in a flow section that lies above the hydraulic grade line. So to illustrate further the difference, let us examine this video.
In this lesson, we will discuss the energy grade line and hydraulic grade line. Here we have the conservation of energy equation for a control volume with one inlet and one outlet when the flow is steady and one-dimensional. All terms have units of length and are called heads. We now define two new quantities called the energy grade line, or EGL, and the hydraulic grade line, or HGL, which will help us visualize the mechanical energy in a flow. EGL is the pressure head, P over gamma, plus the velocity head, V average squared over 2G, plus the elevation head, Z, and will represent the total mechanical energy in the flow. HGL is just the pressure head plus the elevation head, and will represent the total potential energy in the flow. EGL minus HGL gives the velocity head, the term representing the total kinetic energy in a flow. Here's an example of how the energy grade line and hydraulic grade line can help us visualize how the mechanical energy in a fluid changes as the fluid flows through various devices. On the left, we have a large reservoir that is connected to a pipe system. The liquid level at the top of the reservoir is a distance L from the ground. We will assume that the reservoir is so large that the height does not change significantly in time, which means we have a steady flow situation. At the top of the reservoir, the flow speed is 0, the gauge pressure is 0, and the elevation is L. Since the velocity is 0, both the EGL and HGL curves at the top of the reservoir are equal to the height L. When the liquid travels through the sharp-edged entrance into the pipe system, the liquid will gain velocity and will experience frictional loss due to separated flow at the entrance. The frictional loss causes a steep decline in the total mechanical energy, which is represented by a steep decline in the EGL. However, the HGL declines more rapidly than the EGL since some of the potential energy of the liquid also is converted into kinetic energy. In the section of straight pipe, the pressure drops gradually due to friction caused by the pipe wall. Since the flow speed is constant in the pipe, the slope of the EGL and HGL curves decline by the same amount. At any point along the flow, the distance from the ground to the fluid is the elevation head Z. The distance from the fluid to the HGL curve is the pressure head P over gamma, and the distance between the HGL and EGL curves is the velocity head V average squared over 2G. Both the EGL and HGL curves drop rapidly at the valve, since valves usually induce separated flow, causing a rapid loss in pressure head. After the valve, the EGL and HGL curves continue to decline due to pipe friction. Pumps boost mechanical energy, primarily through an increase in pressure, and so both the EGL and HGL curves rise sharply at the pump. After the pump, fluid travels through a pipe and then a nozzle. Nozzles accelerate flows while lowering pressure, usually without inducing significant flow separation. This means that the EGL curve declines gradually through the pipe and nozzle. The HGL curve declines at the same rate through the pipe, but then drops rapidly at the nozzle since the velocity head increases at the expense of the pressure head. Following the nozzle, the liquid travels through a smaller diameter pipe, resulting in a more rapid drop in pressure and steeper EGL and HGL curves. Turbines extract mechanical energy from flows, so both the EGL and HGL curves decrease sharply at the turbine. Following the turbine, the EGL and HGL curves decrease gradually due to pipe friction. Since the pressure at the exit of the pipe system is atmospheric, which is 0 gauge, the HGL curve is just the elevation at the exit. The HGL curve can be observed by creating a series of static pressure taps along the pipe system. The height of the liquid line in the pressure taps will be equal to the hydraulic grade line at those points. The EGL curve can be observed by using a series of L-shaped tubes, which are called pitot tubes, in the pipe system. The height of the water line in the pitot tubes is equal to the energy grade line at those points. In this example, the HGL and EGL curves are shown as changing sharply when encountering a new device. In reality, the shape of the curves will be smoother. However, this example does show the general behavior of the HGL and EGL curves. In this lecture,
us to understand the application of the Bernoulli equation, let us answer this example. Water is flowing from a hose attached to a water main at 400 kilopascal gauge. A child places his thumb to cover most of the hose outlet, causing a thin jet of high-speed water to emerge. If the hose is held upward, what is the maximum height that the jet could have achieved? So you can see here the illustration of this problem. So the child places his hands in order to uh, increase the speed. That's why there is a sudden uh, formation of a water jet. So what we'd like to get is the maximum height that this jet could achieve. So we have a water from a hose attached to the water main is sprayed into the air, and the maximum height the water jet can rise is to be determined. So in this example, for us to be able to apply the Bernoulli equation, the flow exiting into the air would be considered as steady, incompressible, and irrotational, so that again the Bernoulli equation is valid. The water pressure in the hose near the outlet is equal to the water main pressure of 400 kilopascal. So that's why P1 would be 400 kilopascal. The surface tensions effects would be negligible. The friction between water and air would also be negligible. The irreversibilities that may occur at the outlet of the hose due to abrupt expansion would also be considered as negligible. So from the given, we have a P gauge of 400 kPa. The unknown is the Z2, or the height, the difference between Z1 and Z2. So from the Bernoulli equation in the form, so we have this Bernoulli equation from between one point and another point. So we can see that it should be, the value would be, the summation of each term would be constant. So that's why we have this Bernoulli equation. So the velocity inside the hose is relatively low. So we can consider that as, so that our V1 would be equals to 0. We take the hose outlet as the reference level. So that's why Z1 would also be 0. So meaning the measurement here would be 0, then up would be positive Z. At the top of the water trajectory, since it would stop its increase in height, the V2 would be equals to 0. The atmospheric pressure pertains at 2. P2 would be equal to atmosphere because it's exposed now to the atmosphere. So that's why from this equation, we can cancel out some of the terms, such as the V1 squared over 2G and the Z1, because this would be equals to 0. And in here, our P2 would be equals to ATM, and we can cancel out V2 squared over 2G. So that's why we have this one left from the Bernoulli equation. And then we are going to rearrange this so that we can solve for the value of Z2, which is what we are looking for. So that's why our Z2 would be equals to P1 minus PATM over rho G. And since P1 minus PATM is just equals to gauge, right? Because if P1 would be the absolute, then absolute minus ATM is the gauge. So that's why we have P gauge over rho G is equals to Z2. The reason why we express it in gauge because we are given with P gauge. So we solve for Z2 by substituting the values. We just express this in the uniform dimension. So that's why our unit here would be Pascal. So Z2 is 40.7747 meter. So as you can see, it's a very long increase in water jet. So maybe that's the one that is used for water fountain, for example, in order to achieve such height, which is 40.7 meter. So this problem involves the conversion of flow, kinetic, and potential energies to each other without involving any pumps, turbines, and wasteful components with large frictional losses, and thus it is suitable for the use of the Bernoulli equation. The water height that we have obtained here is the maximum, because this is the ideal situation. So meaning, if there would be other reason that it would cause the reduction of the height. So meaning this 41 meter would be the maximum height that is possible because the Bernoulli equation is the ideal. So again, the result obtained by the Bernoulli equation represents the upper limit and should be interpreted accordingly. It tells us that the water cannot possibly rise more than 40.7747 meter, and in all likelihood the rise would be much less than this value due to irreversible losses that we have neglected in the assumption. So we have another example. We have here a large tank open to the atmosphere filled with water to a height of 5 meter from the outlet tap. A tap near the bottom of the tank is now opened and water flows out from the smooth and rounded outlet, and we are to determine the water velocity at the outlet. So here we have a tap near the bottom of the tank is open. As you can see, it's open now. The exit velocity of water from the tank is to be determined, so that's the V2. Our assumption here would be the flow is incompressible and irrotational, except for those very close to the wall. The water drains slowly enough that the flow can be approximated as steady. So it's steady flow. Actually, it's quasi-steady when the tank begins to drain. So this problem involves the conversion of flow, kinetic, and potential energies to each other without involving any pumps, turbines, and wasteful components with large frictional losses, and thus it is suitable to use the Bernoulli equation. So we have here the given Z1 is equals to 5 meters. So we selected point 1 to be the surface and point 2 to be the exit. So it's actually up to you what would be the reference level. So Z1 is 5 meter. The unknown are the speed or the water velocity at the outlet, or V2. So from the Bernoulli equation in the form that you can see in the presentation, the value would be the same from the inlet and the outlet. The summation of those energy would be the same. So let point 1 be the free surface of the water, so that our P1 is exposed to the atmosphere. So P1 is equals to P ATM. Since the tank is large relative to the outlet, V1 would be equal to 0 because it would be very small. Now the speed of the velocity here at point 1 would be considered as negligible. We take the reference level at the center of the outlet Z2, so that's why Z2 would be equals to 0. Since the water discharge in the atmosphere, P2 would be equal to P ATM. So P1 is equals to P2 and they are P ATM. So therefore our Bernoulli equation would be reduced because we can cancel out some terms. So P1 will be equal to P ATM. We can cancel out the V1 squared over 2G because V1 is 0. Z1 is 5 meter. And then P2 is P ATM. V2 squared over 2G would remain because we will measure V2. And then Z2 would be equal to 0 because it is our reference level. It is our point 0. So rearranging the term to solve for V2, we would see that from this form we would have V2 would be equals just to square root of 2G Z1 because we can cancel out also the P ATM over rho G because they are found in both sides of the equation. So our speed at the outlet would be square root of 2G Z1. So solving V2 by substituting the value, the water velocity at the outlet would be 9.9045 meter per second. So this square root over 2G Z1 is also known as the Torricelli equation. It's a very famous equation that will help us actually solve readily the velocities. So therefore the water leaves the tank with an initial velocity of, if you're going to compute the initial velocity, that would be this initial velocity would be around 9.9 meter per second. So this is the same velocity that would manifest if the solid were dropped a distance of 5 meter in the absence of air friction in the absence of friction drag. What would be the velocity if the tap were at the bottom of the tank instead of the side? So what would you think would be the answer? So if the orifice were sharp edged instead of rounded, then the flow would be disturbed and the velocity would be much less than 9.9 meter per second, especially near the edges. So care must be exercised when attempting to apply the Bernoulli equation to situations where abrupt expansions or contractions occur, since the friction and flow disturbances in such cases may not be negligible. But in this case, we consider it as negligible. That's why this 9.9 is the maximum velocity that we can actually obtain. So we have here another example. So during a trip to a beach with atmospheric pressure of 1 atm, a car runs out of gasoline and it becomes necessary to siphon gas out of a car of a Good Samaritan. The siphon is a small diameter hose, and to start the siphon it is necessary to insert one siphon end in the full gas tank. We fill the hose with gasoline via suction and then place the other end in a gas can below the level of the gas tank. The difference in pressure between point 1 at the free surface of the gasoline tank and point 2 at the outlet of the tube causes the liquid to flow from higher to a lower elevation. Point 2 is located 0.75 meter below the point 1 in this case, and point 3 is located 2 meter above point 1. The siphon diameter is 5 mm, and frictional losses in the siphon are to be disregarded. Determine the minimum time to withdraw 4 liters of gasoline from the tank to the can and the pressure at point 3. And we take the density of gasoline as 750 kilogram per meter cube. So this is the illustration. So we wanted to siphon a gas in order to fill the car that runs out of gasoline. So we have here point 3, the highest point, and then we have point 1. The difference between point 1 and point 3 is 2 meter, and then we have point 2 here below point 1 would be 0.75 meter. So gasoline is to be siphoned from the tank, and the minimum time it takes to withdraw 4 liter of gasoline, and the pressure at the highest point in the system are to be determined. So the flow is steady and incompressible, even though the Bernoulli equation is not valid through the pipe because of frictional losses. We employ the Bernoulli equation anyway in order to obtain the best case estimate. The change in the gasoline surface level inside the tank is negligible compared to the elevation Z1 and Z2 during the siphoning period. So we take the density of gasoline to be 750 kilogram per meter cube. So our given are the atmospheric pressure, the diameter of the siphoning tube, which is 0.005 meter, the volume of gasoline that to be siphoned is 4 liter, the density of gasoline is 750 kilogram per meter cube. The unknown are the time that would take in order to siphon 4 liter, as well as the pressure at the highest point, which is point 3. So from the Bernoulli equation in the form that you can see in the presentation, we take point 1 to be at the free surface of the gasoline in the gas tank. So you can see here the gas tank, the free surface here would be the point 1. So that P1 is equals to atmospheric pressure, or ATM. Since the tank is large relative to the tube, we can consider V1 to be equals to 0. And we take point 2 as the reference level. If we take point 2 as the reference level, Z2 would be equals to 0. And gasoline discharges into the atmosphere, so that's why P would be equals to PATM at point 2. So the Bernoulli equation from this form would be reduced to this form, because we can cancel out V1 squared over 2J because V1 is equals to 0. And we can also cancel out Z2 because Z2 is the reference level, which is equals to 0. Rearranging, we can actually cancel out PATM over rho G, so that we would obtain V2 over is just equals to 2GZ1, or the Torricelli equation. So we solve for V2, we can obtain 3.836 meter per second. So that's the speed of the gas here at point 2, 3.836 meter per second. So now that we have the velocity, then therefore we can get also the volume flow rate. The volume flow rate is just equals to the area and the cross-sectional area where it flows and the speed of the flow, which we already calculated in the previous slide. The area is just pi over 4, the diameter of the siphon tube squared. So substituting the values, then we can get the volume flow rate as 0.07532 liter per second. So we express this in liter because our given is also in liter. So to siphon 4 liter of gasoline, therefore we can use now that the relationship between the volume flow rate and the volume. So the result would be 53.1070 seconds to siphon 4 liter of gasoline. So it's almost 1 minute. The siphoning time is determined by neglecting the frictional effects, and thus this is the minimum time required. In reality, the time will be longer than 53.1 seconds because of friction between the gasoline and the tube surface. So for the pressure at point 3, so we will use again the Bernoulli equation, now in the form from point 2 to point 3, so that we can analyze that point 3 here. So as you can see, when we analyze point 1 and point 2, it's actually okay to not consider the other point because Bernoulli equation can be applied between 2 points. So any 2 points. So since we already know the data from point 2, then we can use that to get point 3 by using the Bernoulli equation. So since by conservation of mass, V2, the velocity, the speed would be equals along the flow. So V2 would be equals to V3. And also, our Z2 would be the reference level, so that's why it's 0. And P2 is P-ATM. P3 is not equals to P-ATM because it's a closed tube. So by using these values, we can actually cancel out some terms so that P3 would just be equals to P2 minus Z3 raw G, as you can see. So substituting the value, we can get the value of P3 as 81.091 kilopascal. So the pressure at point 3 is below the atmospheric pressure, as you can see. So if the elevation difference between points 1 and 3 is too high, the pressure at point 3 may drop below the vapor pressure of gasoline at the gasoline temperature, and some gasoline may evaporate or cavitate. So the vapor then may form a packet at the top and will halt the flow of the gasoline if that is the case. So we have here another example. So we have a piezometer and a pitot tube are tapped into a horizontal water pipe to measure the static and stagnation pressure, or the sum of static and dynamic pressures for the indicated water column heights. We determine the velocity at the center of the pipe. So what would be the value of V1, or the speed at the center of the pipe? So this is applicable for actual real life scenario wherein you are designing, for example, a piping system, and or say for example you wanted to determine the condition. So that's why you can use the piezometer and pitot tube to know the speed and how you can design the cross-sectional area, for example, of the pipe. So in the figure, we are given here with the corresponding heights in the piezometer tube and the pitot tube. So this one is the piezometer tube, and this is the pitot tube, and then the liquid is the water. The stagnation point is point 2. So the unknown is V1, the velocity at the center of the pipe. So we let points 1 and 2 along the center line of the pipe. Point 1 is directly under the piezometer, as you can see, and point 2 is the tip of the pitot tube. So assuming a steady flow with straight and parallel streamlines, the gauge pressures at point 1 and point 2 would be P1 would be equals to rho g H1 plus H2. So the pressure at point 1 would be the rho g h1 plus h2. So that's the pressure of the water, and the height here at the piezometer tube is h2. So that's the gauge pressure at point 1. For point 2, on the other hand, the pressure would be rho g h1 plus h2 plus h3, because it's the piezo tube. So it's the water, and then we have this height h2 and then h3. So this would be the corresponding gauge pressure in point 1 and in point 2 from the piezometer and the piezo tube. So in this problem, we consider the flow as steady and incompressible, and point 1 and 2 are close enough together that the irreversible energy loss between the 2 points is negligible. So thus we can use the Bernoulli equation. So from the Bernoulli equation in the form, we can see, since point 1 is the stagnation point, so when we say stagnation point, the velocity at that point is equals to 0. That's why v2 is 0. Also, we can see that the elevation of point 1 and 2 is the same, so z1 is equals to z2. So we can cancel out some terms so that we can obtain the value of v1. So the value of v1 can be obtained by substituting the value of p1 and p2 that we already get a while ago. So from the result here, so we can substitute the value of p2 and also p1, so that's why we have this term. If you're going to solve that, that would just be equals to h3. And since v1 squared over 2g is equals to h3, then v1 would be square root of 2g h3. So therefore, the speed at point 1 or at the center would be 1.534 meter per second. So note that in this problem, just to determine the flow velocity, all we need to measure is the height of the excess fluid column, because h3 here is the excess fluid column. As you can see, it's the 12 cm. So in order to get the velocity, flow velocity, if for example you are doing this in actual scenario, and then you have the piezometer and piezo tube, then you just measure the height in the piezometer, and then you measure the height at the piezo tube, and then you get the difference of the head. So that difference would be the h3. That's the only requirement in order to get the flow velocity, as you can see in this example. And then we have another example. We have a hurricane is a tropical storm formed over the ocean by low atmospheric pressure. So as you can see, the reason why there are hurricane is because there are LPA, or low pressure areas. As a hurricane approaches the land, inordinate ocean swells or very high tides accompany the hurricane, which we also experiences, right? A class 5 hurricane features winds in excess of 155 miles per hour. Although the wind velocity at the center eye is very low, these figured effects depict the hurricane hovering over the ocean swell below. So the atmospheric pressure is 200 miles from the eye, which is point 1. So the point 1, which is 200 miles from the eye, the atmospheric pressure is recorded as 30-inch mercury. So here there is actually a normal ocean level because it's far from the eye. So the hurricane atmospheric pressure at the eye, so here at the eye, below it, the pressure would be 22-inch of mercury. So we wanted to estimate the ocean swell at the eye of the hurricane at point 3, and also at point 2, where the wind velocity is 155 miles per hour. So in this problem, we take the density of the seawater and mercury to be 64 pound mass per feet cube and 848 pound mass per feet cube respectively, and the density of air at normal sea level temperature and pressure is 0.076 pound mass per feet cube. So the normal sea level temperature is this point 1 here, which is where the calm ocean level. So the density here is 0.076 pound mass per feet cube. Point 3 again is directly below the eye. So that's why the speed here, the wind speed here would be almost 0, or considered to be 0, because at the eye it's actually the speed is actually 0. So we thought now that the velocity at the eye would be the the strongest, but in the truth is that it's the velocity here, the wind velocity at the eye is very low and can be considered as zero. At point 2, since it is away from the eye, the wind speed is 155 miles per hour. So as a result of that, there would be dynamic effects, the velocity head. So that's why the height of the ocean is greater at point 2 because there is a wind speed here. At point 1, since there's no effect of at all because it's very far from the hurricane, it's just generally calm. So the hurricane is moving over the ocean. The amount of ocean swell at the eye and at active regions of the hurricane are to be determined. So our assumption is that the airflow within the hurricane is steady and compressible and irrotational so that the Bernoulli equation is applicable. This is certainly very questionable assumption for a highly turbulent flow such as a hurricane, but it will be justified later on in the solution. The effect of the water drifted into the air would be considered as negligible also. The densities are also given in the problem for us for our use later on. So we are given with the density of mercury, the density of seawater, the density of air at normal or the calm sea level, the atmospheric pressure at point 1, which is the calm ocean level, is 30-inch mercury. And we are also given with the atmospheric pressure at the eye, which is the point 3, is 22-inch mercury. And the velocity of wind at point A or point 2 is 155 miles per hour. We will get the head, the ocean swell at directly below the eye, which is H1, and the ocean swell direct 55 this at point A. So we reduce the atmospheric pressure over the water causes the we reduce atmospheric pressure over the water causes the water to rise. So thus decreased pressure at point 2 relative to point 1 causes the ocean water to rise at point 2. The same is true at point 3 where the storm air velocity is negligible. The pressure difference given in terms of the mercury column height can be expressed in terms of seawater column height by the relationship delta P, or the change in pressure between different points between seawater and mercury can be expressed in this form. So rho GH of seawater is equals to the rho GH of mercury because they will just be equals delta P. So if we cancel out the value of gravity, then we will obtain this equation. And in that, the ocean swell at the eye of the hurricane at point 3, as you can see, is the H1. So we can get that by knowing that this fluid is actually seawater. So H1 is the head of the seawater at point 1. We can compute using rho density of mercury times the head of the mercury divided by the density of the seawater. So for the density of mercury, it's given as well as the density of seawater. But for the head of the mercury, the reading would be the difference between the 30-inch mercury at the point 1 and 3 because our at normal condition would be the point 1. So that's why to get the elevation head for mercury, we would subtract the value at that point, which is 30-inch Hg, minus at that point rather. So that's 22-inch Hg. So normal minus the at the eye, which is below the eye. So H1 or the ocean swell below the eye would be 8.8 feet seawater. So that's the height of water at that point. So 8.83 feet is the storm surge at the eye of the hurricane since the wind velocity there is negligible and thus there are no dynamic effects. So here we just get it directly using the change in pressure. To determine the additional rise of ocean water at point 2 due to the high winds at that point, we write the Bernoulli equation between points A and B, which are on the top of the points 2 and 3 respectively. So from the Bernoulli equation in that form, we can between point A and B, which is below the point, which is actually the representing the two heads here. Since the eye of the hurricane is relatively calm, the velocity of B would be equal to 0. Since both points are on the same horizontal line, ZA and ZB would be equals to 0. So the good thing about Bernoulli equation is we can apply it at the same horizontal level here. So based on this information, then we can reduce our Bernoulli equation into this form, that the V squared over 2G is just equals to the delta P of B and A divided by rho G is just equals to the head of air. So it's, if we use the density of air, then we can get the head of air. So the head of air, if we substitute the value of the speed of air, so it's VA squared over 2G, so that's the speed of air is 155 miles per hour at point A, divided by 2G, which is 32.2, and we just convert the miles per hour to feet, feet per second. It's actually feet per second. Okay, so we have the value 802.5278 feet of air. So in terms of air head, the head of air is 802.5278 feet of air. So since we are not to get the air but the head of the water or the seawater, we will have to get the relationship between them. So the density of an ideal gas at constant temperature is proportional to the absolute pressure and the density of air at the normal atmospheric pressure, which is 14.7 psia. And the value in the given is 30-inch mercury. And it's given also as 0.076 pound mass per feet cube. So the density of air in the hurricane, if it is proportional, then would be PATM over the PATM of that air multiplied by the density of ATM of air. So if we substitute the value from the given that we have here, our PATM is 22-inch mercury divided by 30-inch mercury, which is the PATM of air, and then the normal density of air is 0.076. Then the density of air at the eye, near the eye, would be 0.0557 pound mass per feet cube. So as you can see, there is a reduction in the density of air because of the presence of the hurricane. So the additional water column height at point A due to wind velocity is the H dynamic, or the dynamic head, is equals to the seawater rise, at the additional seawater rise, and that is also equals by the same relationship that we used to get the seawater height at H1, would be also the same way that we can get also the H dynamic due to air, the wind speed due to the wind speed. So that's why by substituting those values that we calculated in the previous slide, we can get the dynamic head as 0.6984 feet of sea water. So the total storm surge at point 2 becomes H1 plus the H dynamic is equals to 9.5134 feet. So as you can see, this problem involves highly turbulent flow and the intense breakdown of the streamlines, and thus the applicability of the Bernoulli equation in some part of this problem is actually questionable. Furthermore, the flow in the eye of the storm is not irrotational, and the Bernoulli equation's constant changes across the streamlines. So that's why it's really questionable to apply it. The Bernoulli equation analysis, however, can be thought of as a limiting ideal case and shows that the rise of seawater due to high velocity winds cannot be more than 0.70 feet or 0.6984 feet of sea water. The wind power of hurricanes is not the only cause of damage to coastal areas. Ocean flooding and erosion from excessive tides is just as serious as are high waves generated by the storm turbulence and energy. So that's why we really have to consider all of this and taking precautions because of the hurricane. So now that we already learned the Bernoulli equation and its limitation as well as application, it is time to ask for us to learn the third conservation law, which is the general energy equation. One of the most fundamental laws in nature is the first law of thermodynamics, also known as the conservation of energy principle, which provides a sound basis for studying the relationships among the various forms of energy and the energy interaction. It states that energy can neither be created nor destroyed during a process. It can only change forms. Therefore, every bit of energy must be accounted for during the process. So that is the reason why we have this general energy equation, because the change in energy content of the system is equal to the difference between the energy input and the energy output. This is the conservation of energy principle for any system, which can be expressed in the equation energy in minus energy out is equals to the change of energy in the system. The energy content of a fixed quantity of mass, whereas the closed system, can be changed by two mechanisms: the heat transfer, denoted by the symbol Q, and the work transfer, denoted by the symbol W. For compressible system, the total energy consists of internal energy, potential energy, and kinetic energy, given by this relationship. So the total energy is equals to the internal energy plus kinetic energy plus the uh, kinetic energy. So as you can see, it's similar to the mechanical energy. The only difference is in total energy, we replace the flow energy with the internal energy, or the U. That's the internal energy. So say for example, to illustrate the conservation of energy principle, so we have here the various work heat interactions. We have a Q in, or there is a heat input of 15 kilojoules. Say for example, this is the system. This is a closed system wherein there is a heat input of 15 kilojoules and a output, meaning it's releasing heat at 3 kilojoules. At the same time, there is a shaft that produces or inputs 6 kilojoules of energy into the system. So here, the energy change of a system during a process would be equal to the net work and heat transfer between the system and its surroundings. So that's why we have the delta E would be the 15, which is the input, minus 3 joules, which is the output, plus another input, which is the work shaft. So the delta E would be 18 kilojoules in this case. So it can be written also in the form the rate of net heat input plus the rate of net work input is equals to the rate of change of the energy in the system, where the rate of heat input or net input would be equals to Q in minus Q out. So we take Q out as negative, and also the work net input would be the total work input minus the total work output. So we take the output as negative. The first way by which energy change is by energy transfer by heat, or Q. So sensible and latent forms of internal energy are actually called thermal energy. So in physics we call them sensible or latent form of internal energy, but they're actually thermal energy. The change in the thermal energy of a given mass results in a change in temperature also. So the thermal energy moves naturally in the direction of decreasing temperature. So that's why the term heat transfer, which is the transfer of thermal energy from one system to another, is a result of a temperature difference between that point and another. So here, the time rate of heat transfer is called the heat transfer rate. So the direction of heat transfer is always from a higher temperature body to a lower temperature one. So that is the reason why, if say for example you air condition the room and the outside of the room is hotter than the air conditioned room, therefore there is a tendency for the hot air in outside the room to enter into the air conditioned room, because that's the natural flow of uh, fluid or air. It's from a higher temperature to a lower temperature. But we have this process called a diabatic process, wherein there is no heat transfer at all. So an adiabatic process should not be confused with an isothermal process, because even though there is no heat transfer in an adiabatic process, the energy content and thus the temperature of a system can still be changed by other means, such as work transfer. So that's why it doesn't mean that it's adiabatic, it will not change its temperature. On the other, isothermal, there is no change in temperature at all. But adiabatic can still be changing its temperature because of work transfer. So what is work transfer? So work is the energy interaction between associated with a force acting through a distance. So that's what we learn from physics. Example is a rising piston, rotating shaft, electric wire crossing system boundary. These are examples of energy interactions with a force acting through a distance. Power, on the other hand, is the time rate of doing work. So for heat transfer, the rate is the heat transfer rate. For work, it is power. Example of work consuming device, meaning it consumes, take in work in order to function, are compressors, pumps, fans, and mixers. They transfer energy to the fluid. On the other hand, we have work producing devices such as car engines, hydraulics, steam, and gas turbine. They extract energy from the fluid. Other forms of work are shaft work, pressure work, and viscous works. So the energy equation for steady and compressible flow is given by this general equation that you can see in the slide. So we have here the terms on the left side and the terms on the right side. So this is actually derived already. So this is the energy equation for steady and compressible flow. If you wanted to know the derivation, you can check the reference, how this equation is determined. But for us, we will just use it now. So here in this equation, the H pump U, or the head pump useful, can be written also in or determined using this formula that you can find here in the presentation. Same also with the head turbine extracted. The HL, on the other hand, which is a loss or head loss, is also given here. And alpha is the kinetic correction factor, kinetic energy correction factor. So for fully developed turbulent flow, our kinetic energy correction factor would be equal to 1.05. So we will use this equation in solving other quantities that we'd like to get in a system, for example. So let us have an example. So we have here the pump of a water distribution system is powered by a 15 kilowatt electric motor whose efficiency is 90%. The water flow rate through the pump is 50 liter per second. The diameters of the inlet and outlet pipes are the same, and the elevation difference across the pump is negligible. If the pressures at the inlet and outlet of the pump are measured to be 100 kilopascal and 300 kilopascal absolute, respectively, determine the mechanical efficiency of the pump and the temperature rise of the water as it flows through the pump due to the mechanical inefficiency. So the pressure across the pump are measured, the mechanical efficiency of the pump and the temperature rise of the water are to be determined. So our assumptions are the flow is steady and incompressible. The pump is driven by an external motor so that the heat generated by the motor is dissipated to the atmosphere. The elevation difference between the inlet and outlet of the pump is negligible, so Z1 is equal to Z2. The inlet and outlet diameters are the same, and thus the inlet and outlet velocities and kinetic energy correction factors are equal. So V1 is equal to V2, alpha 1 is equal to alpha 2. So point 1 is the inlet of the pump, point 2 is the outlet of the pump. So the volume flow rate would be the same because it is one streamline only. So the motor is the one that drives the pump, so meaning it's inputting electric power here in order to rotate the impeller of the pump. So the given are the volume flow rate 50 liter per second, the efficiency of the motor 90%, the electric input from the motor, which is 15 kilowatt, and the pressure at point 2 as well as the pressure at point 1 respectively. The unknown are the efficiency of the pump, mechanical efficiency of the pump, and the temperature rise of the water as it flows through the pump. So the mechanical efficiency of the pump is determined using the formula that we have in the previous slide, as you can see here. So the mass flow rate of the water is to be computed first, and that is equals to the density of water multiplied by the volume flow rate of the water, so that the mass flow rate of the water and flowing in the pump is 50 kilogram per second. So we take the density of the water to be 1 kilogram per liter. That is equals to 1000 kilogram per meter cube. The mechanical power the motor delivers to the pump from this motor can be computed using this formula that we have also in the previous slides. So that is the pump power from the shaft, and then we have the electric input from the motor. So this here, the numerator represents the output, and the input is the input from the motor. So the input from the motor is the 15 kilowatt, and this shaft, the rotation that causes the rotation of the pump, the power that is transferred through that shaft is the one that enters the pump. So that's the efficiency of the motor. So this is the value, this is the same quantity here that you can see here. So from that we can get the pump shaft power by rearranging this formula. So that's equals to the mechanical efficiency of the motor times the electrical power input from the motor. So since we already know those values, we know the efficiency of the motor and the electric power input from the motor, then we can get the shaft power input to the pump. So the power that you put into the pump from the motor, that is 13.5 kilowatt. And the increase in the mechanical energy of the fluid as it flows through the pump by using the point 1 and point 2 can be determined by using this formula. So that is the mechanical energy out minus mechanical energy in, or mechanical power out minus mechanical power in. So that's the change in mechanical energy of the fluid. As you can see, there will be an increase in the mechanical energy of the fluid because of the shaft power input to the pump. So the output will be greater than the input. So that's why we can write that also in terms of the mechanical energies that you can see here. But here we included the correction factor alpha. So do not be confused, this is the one that represents the mechanical energy, these quantities here, between the output, point 2, input or inlet of the pump, 0.1. So since Z1 is equal to Z2, so we neglect the difference between the elevation difference between the inlet and outlet of the pump, as well as the velocities. We take them as the same, as well as the correction factors would be the same. Therefore, it will reduce into this form. The change of mechanical energy of the fluid, therefore, can now be computed by substituting the value of P2 minus P1 divided by the density and multiplied by the mass flow rate that we calculated already. Then we convert it into kilowatt, so the result would be 10 kilowatt. So the change in mechanical energy of the fluid is 10 kilowatt. So therefore, we can get the efficiency of the pump using the formula, the change in mechanical energy of the fluid divided by the power pump shaft input, so which is from the motor. So that's 10 kilowatt mechanical energy of the fluid, change in mechanical energy of the fluid divided by shaft pump power input, 13.5 kilowatt. So the efficiency of the pump is 74.1%. So we can see that the 25% here would be the inefficiency of the pump. The temperature rise of water due to its mechanical inefficiency is determined from the thermal energy balance. So because there is a loss, meaning this loss now would be the inefficiency, so that we wanted to get the temperature rise because of that inefficiency. So we can use the thermal energy balance by using the mechanical energy loss. The definition of mechanical energy loss is the change in internal energy multiplied by the mass flow rate, or it is also equals to mc delta T. So rearranging this term, we can get the delta T as EMEC loss divided by the mc. So for mc, we take the value of C for water as 4.18 kilojoules per kilogram Kelvin. On the other hand, for the mechanical energy loss, it's just the difference between what's inputted into the shaft of the pump, which is 13.5 kilowatt, and what is actually delivered to the fluid, or the change of mechanical energy of the fluid, which is 10 kilowatt. That's why it's 13.5 kilowatt minus 10 kilowatt is the loss. So we have loss of 3.5 kilowatt. So because of that loss, there would be a change also of the temperature. There would be a temperature rise. So by calculating, we got it as 0.0167 Kelvin. So therefore, the water will experience a temperature rise of 0.016 Kelvin due to mechanical inefficiency, which is very small as it flows through the pump. So that's how we analyze the pump motor connection using the third conservation law, which is the general energy equation. And then we have here another example. In a hydroelectric power plant, 100 meter cube per second of water flows from an elevation of 120 meter to a turbine where the electric power is generated. The total irreversible head loss in the piping from point 1 to point 2, excluding the turbine unit, is determined to be 35 meter. If the overall efficiency of the turbine generator is 80%, estimate the electric power output. So the available head, flow rate, head loss, and efficiency of the hydroelectric turbine are given. The electric power output is to be determined. So our assumptions here is that the flow is steady and incompressible. The water levels at the reservoir and the discharge site will be constant. So meaning at the reservoir at point 1, at here at the discharge site, the water would be still, so the speed would be 0, and we take the density of water to be 1000 kilogram per meter cube. So this is the illustration of this hydroelectric power plant. So the given are the volume flow rate, which is 100 meter cube per second, the Z1, so we take Z1 as the surface from the dam reservoir, that is point 1, that is 120 meter from the surface, also at the discharge site. So Z1 is 120 meter. The head loss is 35 meter, which is given. This is due to the piping system from point 1 to point 2. And then we have the efficiency of the turbine generator. It's combined, it's 80%. And we have to get the electric power output. So electric power output of the turbine, of the generator, because we are given with the turbine generator. So from the energy equation for steady and compressible flow, so we will use that equation. We take point 2 as the reference level, so Z2 would be 0. So this is the ground, so we take it at 0. Point 1 and 2 are exposed to the atmosphere, so P1 and P2 is equals to P ATM. The velocity of water at point 1 and 2 is negligible because we take it them as still water, so they are 0. So the energy equation would be reduced to Z1 is equals to H turbine extracted plus HL. So you can see that we can cancel out P1 over rho G and P2 over rho G because they are both P ATM. We can also cancel out this V1 squared over 2G and this V2 squared over 2G because V1 and V2 is equals to 0. And also we do not have pump here, so H pump would also be 0. And what remains are the head turbine extracted and the head loss. So rearranging that, we can get the head turbine extracted, Z1 minus HL. And that is 120 meter minus 35 meter is 85 meter. So based on this head, we can get the value of the power because there is a relationship between head and power. So here this is related by the power extracted by the turbine from the water would be equals to M mass flow rate, G, and the turbine head extracted. And since we know that mass flow rate is equals to density times volume flow rate, then the equation would be in this form: density, volume flow rate, G, and the head of the turbine extracted. So the power, the turbine power corresponding to that head extracted is, by substituting the value, would be around 83.385 megawatt. So the electric power generated by the actual unit can be computed using the turbine generator efficiency. So here the turbine runs the generator. So therefore the input now to the generator would be this value that we calculated from the turbine. That would be the input. And the electric power generated would be the output from the generator, because the generator will be the one that will produce the actual power, the desired output. So that's why the combination would be the turbine efficiency, the turbine generator efficiency would be equals to the electric power generated divided by the work turbine extracted. So our input is what is extracted by the turbine. So this is the turbine. The rotation of the turbine rotates the shaft, which is coupled to the generator, which causes the generator to rotate. So that's why the input is from the turbine, the output will be the output of the generator, and that is the power output. That's the W electric here in the numerator. So rearranging that, we can get our desired value, which is the electric power output. So our value by calculating is 66,708,000 watts, or that is 66.708 megawatt. So you can see the electric power generated is 66.708 megawatt. Note that the power generation would increase by almost 1 megawatt for each percentage point improvement in the efficiency of the turbine generator unit. So that is the reason why we have to design them very carefully, in order to increase the efficiency. So here we can produce 66.708 megawatt. We can still increase that because, as you can see, the turbine can actually extract. So the turbine can actually extract 83.385 megawatt. But because of the inefficiency, the power that can be generated by the turbine, the generator, would be 66.708 megawatt. So we have to improve the efficiency of both these devices. And we are down into our last example. Here, water is pumped from a lower reservoir to a higher reservoir by a pump that provides 20 kilowatt of useful mechanical power to the water. The free surface of the upper reservoir is 45 meters higher than the surface of the lower reservoir. If the flow rate of the water is measured to be 0.03 meter cube per second, determine the irreversible head loss of the system and the lost mechanical power during this process. So here, water is pumped from a lower reservoir to a higher one. The head and power loss associated with this process are to be determined. So our assumption is that the flow is steady and incompressible. The elevation difference between the reservoir is constant. We take the density of water to be 1000 kilogram per meter cube. So we are given with the volume flow rate, the pump power input, which is 20 kilowatt. We are given with the Z2. So the Z2 is from Z1 is 45 meter, and the unknown are the mechanical loss in mechanical power, and then the head loss of the system, a reversible head loss of the system. So from the energy equation for steady incompressible flow, so we just actually multiply it with mass flow rate. So that we just multiply that energy equation with the mass flow rate so that we can obtain this formula. So that the result now would be rate, as you can see, so that we can get the mechanical loss here in this term. So taking point 1 as the reference level, so Z1 is equal to 0, point 1 and point 2 are exposed to the atmosphere, so P1 is equal to P2 is equal to ATM, so we can cancel out. The velocity of water at point 1 and 2 is negligible. We take the water as still, calm, so the velocity is 0 at those points. So therefore, this whole equation here would be reduced into this one by canceling the terms that can be cancelled because of this decision here. So by rearranging, we can get the mechanical power loss as the pump power minus the mass flow rate multiplied by G and the Z2. Since mass flow rate is density times volume flow rate, then we have this form. And then by substituting the values from the given, we can get the loss in mechanical power as 6.756 kilowatt. So this is the mechanical power loss of the pump, 6.756 kilowatt. The mechanical head loss is then can be computed by the relationship, which is we already have this in the previous slide. So we just substitute the value. So our head loss, mechanical head loss of the pump is 22.9579 meters. So meaning it can actually elevate the water to almost 23 meters, but because of the head loss, it will not be able to do it anymore. So the head loss will be 22.9579 meter. So the 6.76 kilowatt of power is used to overcome the friction in the piping system. Note that the pump could raise the water an additional 22.957 meter if there were no irreversible head loss in the system. So in this ideal case, the pump would function as a turbine when the water is allowed to flow from the upper reservoir to the lower reservoir and extract 20 kilowatt of power from the water. So in this presentation, we were able to understand the conservation of energy, specifically the conservation loss, mechanical energy and efficiency, the three important equations in the conservation of energy: the continuity equation, the Bernoulli equation, and the general energy equation. I hope that you were able to grasp the information that is presented here. If you have questions, feel free to ask during our synchronous class.